Assalamu alaikum everyone. Today we are going to conduct our third lecture of this online session series, and the topic of this particular lecture is different data types which are available for Intel's 8080, 86 or 8088 microprocessor. Before we go to the different data types which are available for these microprocessor, let's reconsider some of the facts which we learned about in the last lecture, and we consider different data formats. What were those? If you remember, 8086 or 8088 microprocessor can store information as byte, as word, and as a double word. So these were three different data formats which were available for 8086 or 8088 microprocessor, and in these different formats microprocessors can save and retrieve information from memory attached to with these microprocessor. Byte refers to 8 bit of information. That means only one location of the memory will be used. Word means uh, 16-bit of information, or two locations will be used from the memory. And similarly, the double word, or it is also known as a pointer, it refers towards the four different locations which are consecutive locations. uh, and if you remember, there was a very important question from the last lecture, that how these different data types are stored, sorry, how these different formats are stored within the microprocessor's memory. Of course, it is not the physically part of the microprocessor, but it is attached memory. So there were some terminologies which were involved in those uh, mechanisms. One of the terminology was Little Indian, and in Little Indian approach, we stores the lowest byte or the least significant byte of any word or double word at the lower addressed location. Similarly, the high significant byte or the most significant byte stored at higher address. These were the approaches, or these were the mechanism which was used in storage of different data formats within the memory slot. Let's come to the topic of today's lecture, which is the different data types which are available or which can be used by 8086 or 8088 microprocessors. And we're gonna list only those different data types which are recommended in your textbooks. If you are following some other book, you can find various versions of different data types. Of course, there may be some interconversions which you can apply to them. Well, so let's come to the data types which are available. The very first data type is integer type. It's very well known data type which are used in various programming languages. Binary coded decimal BCD is the second data type which can be used when one is storing or retrieving information from the memory slots which are connected to 8086 or 8088 microprocessor. And the third and the last data type which we are going to deal in this particular lecture is ASCII. ASCII is the acronym for American Standard Code for Information Interchange, and we will learn how different information can be stored within these using these different data types in the memory slots which are attached to 8086 or 8088 microprocessor. So let's consider very first integer data type. And when one is considering integer data type from the point of view of 8086 or 8088 microprocessor, there are two different integer type which can be used in programming languages when one is going to program 8088 or 8086 microprocessor. And so one of them is unsigned integer data type. What does it mean? We are going to explore in the next slide. And the second one is the signed integer data type. So how unsigned and signed integer data type reflects the different information which can be stored in 8086 or 8088 microprocessor. We are going to deal with them in coming slides. So let's do them one by one. So let's discuss about unsigned integer data type for 8086 or 8088 microprocessor. Uh, what does it mean by unsigned and how it looks like when it is going to store in the memory? Again, there are two different versions of unsigned integer data type. The very first one is byte-wide information. Byte-wide information means the information which is only 8-bit long, and if you have been following this lecture series, you know that 8-bit of information can easily be stored in one slot of microprocessor, one slot of memory which is attached to these microprocessors. So 8-bit information needs only one location which to store. Well, uh, one when one is considering only 8-bit of information, so information starts from this bit and it goes to this most significant bit. If you want to number them, you can number them like D0, D1, D2, D3, D4, D5, D6, and D7. So if in total these will be basically 8-bit of information. If you want to decide uh, that what will be the range of decimal numbers that can be covered by these 8-bit of information, then you can easily calculate it. If you remember, let's consider we have only 2-bit of information, so it can be 0 0 0 1 1 0 and 1 1. I'm sorry for very bad pointing, but let's try to focus. What does it mean? So if we are considering only 2-bit of information, then information can range from 0 0 to 1 1. So in total these are basically how many symbols? 4 symbols, because 2 power 2 is equal to 4 symbols. So now let's consider the same thing. If we are going to deal with uh, let's say we are going to deal with 3-bit information, then one can actually go to the very first information that one is going to number is 0 0 0 and it will range up to 1 1 1. So how many combinations will be there? It will be 2 power 3, which means there will be 8 different combinations which can reside with these 3-bit unsigned binary numbers. Now let's consider and come back to the original situation when we were considering byte-wide information of 8-bit, and when we are talking about unsigned integer data type. So there are 8 different bits which can be used for this purpose. So 2 power 8 means how many different combinations are available is 256. And if we want to really uh, exactly tell that what range will be available, so that will be from 0 to 555. So that's how unsigned 8-bit number is ranges. And so these different decimal number can be stored only in single microprocessor's memory location. So let's consider now the another type of unsigned integer data type, and that is word wide. And if you remember, word means 2 bytes of information, or in simple words, 16 bit of information, and they actually started from 0 from D0 to D15. The least significant bit will be D0, and the most significant bit will be 15, D15. So if one is interested to calculate the exact amount or exact amount of numbers which can be represented by which are available for 16-bit unsigned integer data type, so that can be calculated by 2 power 16, and that is basically somehow 65,536, and the range is basically from 0 to 65,535. So why this is known as unsigned? We do not see any negative numbers here. From 0 to 255, we can see there were no negative numbers involved, and similarly from 0 to 65,535, again there are no negative numbers involved. So we are purely talking about unsigned numbers. There will be no negative numbers which can be used in these data types. Well, in this particular slide, we are going to talk about signed integer data type. And like unsigned integer data type, again, there are two different versions of signed integer data type. So what are those? Very first one is very similar, like we discussed in unsigned integer data type, and that is byte-wide information. That means we are using only 8-bit of information, and which can be used only in one memory slot. Well, the situation is almost similar to the previous slide. The information, there are 8-bit of information, so bits can be numbered from D0, D1, D2, D3 and up to D7. Well, the distinction comes here when we talk about this last bit, and that is the sign bit. This means this bit is dedicated to tell you guys that what is the sign of this number, whether it is positive or negative. If this bit is 0, that means it is a positive number, and if that is 1, that means this number is negative number, which means this bit is dedicated just to sign bit. This is also known as a sign bit. So this bit is dedicated just to tell you about sign. So it will never help you guys to determining the number which are available. So this 7th bit, D7 bit, is not available. Only these bits are available to produce the numbers or to produce the symbols. So how many bits? If we just remove this 1 bit from 8 bits, so there will be only 7 bits. So 2 power 7, that means how many combinations are applied is 128. But if we include the sign bit, so 128-bit numbers with positive sign and 128 numbers with negative sign. So there are 128 positive numbers available and 128 negative number available. Well, if you remember, if you put here a 0, that means we are talking about positive numbers, these 128 numbers. And if we put here minus sign, that means we are talking about these these 128 numbers. Well, before we go, let me clean it so that we can explain. Yeah, so the range goes not from 0 to 255, rather range goes from minus 128 to plus 127. It because if you remember, how many negative numbers? 128 numbers. So they definitely range from 1 minus 28 to minus 1. And when we talk about the positive numbers, we can't simply go from 1 to 128. Rather, we have to let me change the color so that you can imply. Rather, we have to go from 0 to 127. That means signed integer data type, and when you are considering only byte wide information, range is basically from -128 to -1 and 0 to 127. So in total it becomes -128 to +127. So these are the numbers which are available in 8-bit signed information. Well, let's consider the next type. First, let me delete the stuff so that explanation becomes more easy for you guys. Well, 16-bit information, it's quite easy and it's almost similar. Again, you have 16-bit of information. The distinction is here again this signed bit. So this bit is again dedicated for sign bit. Yes, sign bit. So these 15 bits will be available for numbers. So 2 power 15, that means 32,000 something numbers will be available, and the range will be from -32,768 to +32,767. And the logic is quite similar that we applied in this 8-bit information. I hope when we are going to take an example, things will become more clear to you. Let's take an example of a memory chip where data is stored, and just to explain you guys, I hope you remember we have done the similar kind of examples in the last lecture as well. This is address column and this is the content column, which means uh, all of this information is just address of the location, while this information written here is just content of that specific memory location. So let's come to the question. What this says: signed word stored at the memory location. We have to find the word which should be signed. Remember, a word should be of 16-bit and it should be signed, which is stored at the location 07 to 06. So if we consider here, this is the location 07 to 06 and the information stored here is BE in hexadecimal. Well, this is not complete word, so it is only just 1 byte and it needs 1 more byte, and that 1 more byte will be stored in the next consecutive location, which is 07 to 07 hex, and the content is FE. So which one of them will be least significant byte and which one of them will be most significant? Least significant byte will be stored at the lower address. The lower address is this one, 07 to 06. So the lowest byte will be BE, and the higher address is this one, 07 to 07 hex. So the most significant byte will be FE. So the word will be FEBE. Well, the next question is, let's calculate its decimal equivalent. It's the similar kind of example is also given in your book. I'm just trying to make another example so that you can more practice. Well, so decimal equivalent, for that you need to convert that number, that specific word into binary, and that is I just converted it into binary for you. Each hexadecimal number is converted into equivalent. For example, F is equivalent to 4 times 1 and so on. E is equivalent to 1110, P is equal to 1011, and E is again 1110. So can we just calculate the whole decimal number? No, it is a signed number, and this last bit, remember, this last bit is just to indicate whether it is positive or negative, and 1 indicates it will be a negative sign. So a minus sign will comes up here, and to make this complete number negative, we need to use the 2's complement. I hope you remember the number systems and their interconversion. So if you want to go to negative, so we have to convert these bits, binary bits, into 2's complement. So I've just taken the 2's complement. I hope you guys know it. So if That is basically 2's complement. If we convert it into, it becomes minus 322. That's how we can calculate how different data types, sorry, how a signed word can be stored. Well, in this specific slide, we are going to repeat the same example that we have learned that we have done in the last slide, and there will be just a small difference. So I hope you guys can do it yourself. The difference is here. Last time we were doing the calculation, we were calculating the word which is stored at 7270206 hex location, and this time it is unsigned. So last time it was signed, and this time it is unsigned. Well, if we go to through the same procedure, you calculate the word is similar. Of course, the content is same, so word will be same, but decimal equivalent it will not be same. First we have to go to hexadecimal, and then we can directly, this time we can directly convert into decimal equivalent, and this time this bit, this most significant bit, is not being used as the sign bit, so one can easily convert all of them. So 2 power 16 will be the combination. The maximum combination is 65,535, and look, this is in the range. So that's, I hope you can do it yourself, and if you have any confusion, we can remove those confusions during the online session. So in this slide we are going to do or to discuss the next data type which is available for 8086 microprocessor, and that is BCD. BCD stands for binary coded decimal numbers, and there has to be a encoding or decoding pattern, and that's given in this specific uh, table. Well, if you look at carefully, the numbers are used are from 0 to 9. That is why it is known as decimal, because their base is again 10. Only 10 symbols are used, and the difference is that difference between the BCD and the hexadecimal is similar. Is just in hexadecimal you have 16 symbols. You go from 0 to 9, and then you go from A to F. Well, in BCD it is not the case. You do not use alphanumeric symbols, you use just numbers. So numbers are from 0 to 9. 0 will be encoded as 00, 1 will be encoded as 0001, and so on. Similarly, it will go to 9, and it is equivalent to 1001. So, but BCD number in 8086 allows two type of formatting. One is unpacked and second one is packed. So first consider unpacked. What is unpacked? Unpacked means, look, if you count these number of bits, how many bits? 8 bits. 8 bits means one location of memory. So 8 bit of information which is stored in one location will be in this format. Since we know that in binary coded there will be only 4 bits of information, so only from D1, D0, D1, D2 and D3. Let me use the pointer, that will be much clearer. Yes, so D0, D1, D2, D3, these 4 bits will be used. Okay, only these 4 bits will be used. The remaining bits from D4 to D7, D4, D5, D6 up to D7, these bits are not used. So that is why it is called unpacked format, in which the most 4 significant bits are not used here. We're gonna take example and it will become more clear to you. Let's remove and let's proceed to the next thing, that is packed format. And what does it mean? In unpacked format, only these 4 bits were used and these 4 bits were not used. If these bits are not used, that means we're gonna put here 0, here again 0, here again 0, and here again 0. But that is not the case. That means uh, we are not going to use these 4 bits when they are available, and that means we are not going to use these 4 bits. Let's take the format of packed format, so that is like this. Look, from D0, D1, D2, D3, this is just one BCD, and the remaining 4 bits which were earlier not used, now it can be used for another BCD number. So rather storing only one BCD, we are now able to use 2 BCD numbers. So that is the advantage of packed format. The packed format is using 2 BCD numbers instead of one BCD number in same location. Let's take a very simplified example of BCD number when they are being accessed from the memory location. Here we see a single memory slot whose address is 07206 hertz, and the data is stored within that location is 10010001. This time this data is shown in binary. Well, question says packed data stored at 0720 6x. So we are told that it's a BCD number and in the packed format stored at this specific location. So can we determine what is the BCD number? Let's see. If you remember, it is packed BCD number. That means these least significant 4 significant bits are one BCD number, that is just one BCD 1, and this is also a BCD because 4 most significant bits are also BCD. So there are 2 BCD numbers stored here. One is 1001 BCD and the second one is 0001 BCD. So what to do when we want to convert into decimal? So if you want to interested to calculate its decimal equivalent, we need to use the binary BCD coded binary coded decimal encoding format. So this 0001 means single one in BCD, and 1001 is basically 1001 is code for 9, so the decimal equivalent is 91. Look, this is the 9 first BCD and the second one is 1. I hope this is quite easy to understand. If you have any confusion, note it down for the question answer session. Well, in this slide we are going to discuss the third data type of 8086 and 8088 microprocessor, and that is ASCII, and it stands for American Standard Code for Information Interchange. This right side table that you see here, this table is going to be used as an encoding format or decoding format. And how we are going to use it, let's discuss the pattern. The format is H1 and H0. What are H1 and H0? H1 and H0 are given here in this table. This row is basically H1 and this row is H0. H0 is composition of B1, B2, B3, B4, while H1 is composition of B7, B6, B5. So H1 comes first, B1, B5, B6, B7, B6, B5, then H0, B3, B2, B1, and so let's decode or encode a decimal 5 in ASCII. So where is 5? We have to find here. I know it's small, but you can use your textbook as well. This is the same table. Actually, I've taken that same table from your book, so you can do it in your book as well. So this is the 5. We have to just find the column number and the row number, and if you see it's 3 here. Yeah, it's 3. 3 means 011, so the code will be 011 I'm sorry, it's 011, not 111. Let me delete it, or let me use the different color. It could become quite easy. So 5, the column is 3, and 3 means 011. It is just the combination, right? And then h naught value, and it is in the row. Look, h naught, and it's 5. 5 means 0 1 0 1. So the code is 011 and 0101, or the ASCII equivalent is 0110101. So when we are going to store it in the memory, it will never be stored as a 7-bit. The last bit will be 0. So the complete 8-bit information will look like this. So that is, and if you want to convert it into hexadecimal, this becomes 3 and this becomes 5, that we noted down. So this h are basically, you can easily understand that these h are basically hex. So h naught is the least significant hex number, and h1 is the most significant hex number. So this is how we're gonna use this table for the calculation of, for the conversion of ASCII into hex or hex to ASCII. So that's it about ASCII conversion. So in this slide we are going to deal with an ASCII decoding example, and the data is stored from memory locations from 011 to 01104. These are 5 different locations, and each of them contain 8-bit of information, and we are given that it is in ASCII. So let's decode it. So let's take the very first information, and that is 0100 and 001. So 0100 means it is equal to what? 4, right? 4. So the not this one. So this is the 4 here, and 0001 means 1, and 1 is here. So if we go and intersect these rows and column, we come to the point where they actually gonna meet, and that is A here. So this specific information, which is ASCII information, it is equivalent to alphabet A. Let's take the next location where it gonna bring us. Let's see, the next location is 01001, and h1 is 0101, which means 5. So 5 is here, and this one 0011, that means 3 is here. So if we gonna intersect it, come to this point, and that is what? S. So the next letter is S. I hope you have understand the concept. Let's do one more example, and then we're gonna conclude our lecture. So let's do the different, this one. So or I think we should go in order. Yeah, we should go in order. So let's do this one, and this one is 0100. That means what? 4. It's here. 4 is here. That's the column. And the next one is 0011. That means 3, and 3 is here. So we're gonna make a line which intersect, and they intersect at C. So the third letter is C, and the fourth letter is I, and the fifth letter is I. I hope you can do all of these examples yourself. So that's it for ASCII data encoding and decoding. So that's it for this lecture. I hope you have understand everything. If you have any confusion or anything which you were not able to understand, try to note down on a page, and we will discuss them in question answer session. Thank you so much for listening.